Having looked at the theory behind the integration, we now want to appreciate its application in getting area under a curve. Given a general equation of a curve, y is equal to ax raised to power n plus bx raised to n minus 1 plus and so on, where a, b, and n are constants, and we are told that this curve is bounded by the lines x is equal to m, so that the lower limit is m and the upper limit is n, and the x-axis. So we want the area, the shaded area, bounded by the given lines, the curve, and the x-axis. Then, the area under the curve will be given by the integration of the left-hand side with respect to x. That gives us the area under the curve. So the equation of the curve is generally so therefore we can apply this formula in solving or in getting area under the following curves. Calculate the area under the curve y is equal to x squared minus 3x plus 4, bounded by the lines x is equal to 2 and x is equal to 4. So we can sketch our curve. Assume that the curve takes the following shape. So let this be the equation. Let this be the curve. Bounded if this is the line x is equal to 2 and this is the line x is equal to 4, we have the x-axis. We want the area bounded by the curve y is equal to x squared minus 3x plus 4. So from above, we have found that the area for part 1, the area is the integration with 4 as the upper limit and 2 as the lower limit of x squared minus 3x plus 4 dx with respect to x, which gives us x cubed over 3 minus 3x squared over 2 plus 4x. Limits 2 to 4. This is equal to 4 cubed over 3 minus 24 plus 16 minus 2 cubed over 3 minus 6 plus 8. So this simplifies to 64 minus 8. So that is 56 over 3 minus 24 plus 16 plus 6 minus 8, which is equal to minus 10. And that gives us 8 and 2/3 square units. For the second part, the boundaries are 0 to 3. Substituting into the expression, we get x cubed over 3 minus 3x squared over 2 plus 4x, 0 to 3. That substitutes directly. It's 9 minus 13.5 plus 12. This gives us 7.5 square units. Second example. Find the area enclosed by the curve, the x-axis and the y-axis. So we have the curve y is equal to x squared minus 4x plus 3. So we need to find x-intercepts of the curve. So at x-axis intercept, x squared minus 4x plus 3 is equal to 0. So that x squared minus 3x minus x plus 3 is equal to 0. X into x minus 3 minus 1 into x minus 3 is equal to 0. We have x minus 1, x minus 3 is equal to 0. So the intercepts, we have either x is equal to 1 or x is equal to minus 3. So diagrammatically, this means that given a curve the curve will cut the x-axis at x equal to 1 and at x equal to negative 3. So we want the area enclosed by this curve, the x-axis and the y-axis. So the area in question is the area that is shaded. And this means that we want the range 0 to 1. So our area, therefore, will be given by the integration x squared minus 4x plus 3 with respect to x between x is equal to 0 and x is equal to 1. So this is equal to x cubed over 3 minus 4x squared over 2 plus 3x 0 to 1. That gives us a third minus 2 plus 3, which is equal to 1.33 square units. Just a bit of correction. Either, for this case, either x will be equal to 1 or x is positive 3. So our curve is not as we had initially indicated, the curve will take the shape, the following shape. Cuts the x-axis at 1 and at 3. So that is the nature of the curve. Therefore, the upper limits will change. Our curve, therefore, will have the area that we want will be as follows. We want the area bounded by the curve, the y-axis, and the x-axis. So we check out for the area that satisfies this condition, and we realize that that will be the area bounded by the curve, x-axis, and y-axis. So accordingly, this curve will have the limits between x is equal to 0 and x is equal to 1 as our limits. This gives us an area of x cubed over 3 minus 2x squared plus 3x between 0 and 1. That will be equal to a third minus 2 plus 3, equal to the previous, which will be 1.33 square units. So it's important to identify the correct area that satisfies the conditions that have been set for the area we need to obtain.